Today's topic is something that everybody talks about and everybody knows a little bit about, but not very many people know what to do with it to solve problems, and that is friction. When two surfaces are in contact with each other and one surface is sliding against another, whenever there's motion or there's an attempt to make motion, there's an attractive force between these surfaces that sort of slows that motion down or helps to stop it. And that's what friction is. The details of how friction works and the nuances between one set of surfaces and another are kind of complicated, but we can boil it down to this. All these friction causes have to do with imperfections on the contacting surfaces. And the other thing is there are attractions between the molecules of the two surface materials that also increase friction. If you take a look at what we think of as even a very smooth, polished surface, like this polished metal surface, under magnification you can see that there are pits and scratches and grooves, and under more intense magnification, well, they look like giant craters. And so at the very small level, at the microscopic level, even smooth things have these rough imperfections, and when they slide against each other, like the interface shows here, you're going to have these little peaks that catch on one another. So there's almost a mechanical stoppage of things sliding back and forth. And the other thing that goes on here is some tiny micro welds occur as particles in this surface and particles in this surface form little chemical bonds between one another temporarily. And that's going to have something to do with the fact that it's harder to get things moving to break the initial friction, which we call static friction, than it is to keep them moving once they have started, because you can't reform those bonds that quickly. How big the frictional force is depends, as you might expect, on a few things. One of them obviously would be how rough is the surface. Sandpaper rubbing on sandpaper is going to produce more frictional force, everyone could imagine, than a piece of glass rubbing against a piece of sandpaper. Another factor is how large is the normal force between the surfaces. In other words, if I have a surface here rubbing against another surface here, if I press these things together harder, well, that's going to cause more of those little bumps to catch on one another, and that will increase the frictional force. And then another factor would have to be the area of contact between the surfaces. If I have a big giant sheet of sandpaper rubbing against another big giant sheet of sandpaper, I can imagine that's going to be harder to drag than two tiny pieces of sandpaper. Well, one way we could study frictional force and find a way to quantify this kind of stuff would be to set up a test apparatus like this. Here I've got a gauge, a force gauge that can measure force. This could be like a bathroom scale, actually, if you set it up right, would do this. And here's a block, which has a surface, obviously, right there. And then here's a table or a board or something like that that has another surface. So at this interface, we can study the force due to friction by just measuring the force that it takes to pull things. If we do that, one of the things that we find from this kind of a study is that the frictional force goes down once movement starts, like this. We saw the gauge jump up, and then once it started to move, it backed off a little bit. The highest force that was reached before any movement started, well, that was called the static friction. We call that the static friction. And the static friction will be higher than once it starts moving. Watch what happens to the scale, the force scale, once this object starts to move. That's called kinetic friction. And as it moves along, we see that that's a lower value. The scale on the force gauge has dropped down to a lower value, and that's kinetic friction. If we were to graph what we just saw with time on the x-axis and force on the dependent axis, we'd find that you would pull and pull and pull and pull, and the force required would go higher and higher and higher until you reached a certain maximum point and it would drop off. That's the static frictional force. The kinetic friction will be much lower than that, and it happens after motion starts. We see that decrease. The second observation that's made is the frictional force turns out to be directly proportional to the normal force. We can imagine that that would be true. You push things harder, and you're going to get a bigger force. Here's the force gauge pulling a block of wood. You can see that the value of force here on this scale is about there. Now, if we add a weight to this block of wood, in other words, increasing the normal force, and then pull it, well, we can see that we have a higher value of force. So right there, as opposed to back there, we see an increase in force needed to pull the object when the normal force increases. Well, if we test this with a whole bunch of different normal forces, we find that the force of friction increases in direct proportionality with the normal force. In other words, bigger force normal, a predictable bigger force of friction. And the slope is what we call the coefficient of friction, and it's abbreviated with this Greek letter mu. So the slope of this line that we have here is mu. Force is the coefficient of friction. Force of friction over force normal. That's slope is mu. So if you put that together as the equation of that line, well, force friction is y, force normal is x, and the slope is mu. So force friction is mu times force normal. One way a physics teacher once told me to remember this is force of friction equals u instead of mu, and n for normal. Fun. Friction is fun. He said that's the way you can remember it. Hope that works for you. A third observation that a test like this shows is that the frictional force turns out not to be dependent on how big the surface area of contact is for a given normal force. So here I'm pulling the block of wood laying on its biggest edge on the flat face, and you can see the force of friction right there on the scale. If I tip this thing on an edge so that a smaller edge is facing me and pull it, well, I'm going to find that the coefficient of dynamic friction and moving friction is the same value. And that's because it doesn't matter if I have this big flat face or this skinny narrow face pulling, as long as the force normal doesn't change. Well, the frictional force doesn't change either. So we decided earlier that the surface area of contact must play a role. So what is that role? And here's something for you to think about. Why is this true? Why is it true that the surface area is not a factor in determining force friction? Think about that. When we're doing problems that involve frictional forces, we treat them just like we do any other kind of force, any other non-contact force or contact force when free body diagrams. And so we can model them with vectors. So wherever motion could happen or is happening, frictional force is always directly opposite of that, 180 degrees from that. Let's solve some problems. First of all, here's a fairly simple problem. 30 newtons are required to pull a 500 Newton box across a level floor at constant speed. The question is, what is the coefficient of static friction between the box and the floor? In solving this problem, first of all, we should probably define what we're looking for, and that's mu, coefficient of friction. Mu is force of friction divided by the normal force. So we have to identify what force of friction and what normal force are here. First of all, I'm going to draw a free body diagram as I start to solve this problem by just drawing myself a picture of my box. And I'm going to apply the forces that I know are on it. One thing I know, it tells me, is that there's a 30 Newton force required to pull this box across the floor. And I also know what its weight is. It's a 500 Newton box. So that's actually force normal, because this is on a flat surface. But another thing I know is it's moving at constant speed. If it's moving at constant speed, there's no acceleration. And if there's no acceleration, that means the net force is zero. So these two forces that I have here must be balanced. And they are. The 500 Newton normal force is balanced by a 500 Newton reactive force. And the 30 Newton pulling force is balanced by a 30 Newton force of friction. Well, I already have the two things that I need to establish what mu is here, so I'll just plug them in here. 30 newtons over 500 newtons. Newtons are going to cancel out, and so coefficient of friction is a unitless number. And when I take 30 and divide by 50, I end up with 0.060. So that's the coefficient of friction between these two objects. Here's another problem. We have a 500 Newton object, but now this object isn't being pulled across a flat floor. It's actually sliding down a 30-degree ramp, but it's at constant speed. So here are some pieces of information we can identify here. We know that our net force is 0. We know that the normal force is going to be related to this weight, but it isn't going to be the weight. And again, our object is to find out what is coefficient of friction. That's what we're trying to find here. Transferring over what we know from the previous slide, we know that the net force is 0. We know that the force due to gravity, or the weight, is 500 newtons. And we know, again, it's our objective to find mu. And mu is equal to the force of friction divided by the normal force. Let's draw a free body diagram and model the situation we have here. First of all, I'm going to draw my ramp. There's my ramp. And I'm going to draw a box on top of this ramp. Just as an object, but I'm going to say it's a box. And I know that this ramp has an angle of 30 degrees. That could be important. Here are the forces that are on the box. One is its weight, 500 newtons. There must be a restorative force pushing back on the box from the ramp, Fr. And because this has a coefficient of friction, there's got to be a frictional force that keeps it from sliding down the ramp. Well, it's moving at constant speed, so F net equals 0. We can use that maybe to solve our problem. We need to know what the force of friction is, and we also need to know what the normal force is. Well, the normal force, we're only going to find that by taking this weight and dividing it into two components. So let's remodel this. Here's my ramp again. There's my box. Here's the frictional force. Instead of the force due to gravity, or the weight, I'm going to replace that with the normal force, and I'm going to replace it with a parallel force. And the reactive force I'm going to put up here. I'm just going to slide it up a bit. There's my reactive force. Now, if there's no net force, if F net is 0, then that means a couple of things. One thing it means is that the reactive force is equal to the normal force. And the other thing that it means is that the force parallel, well, that's equal to the force due to friction. Those two things must be true. So how can that help us solve this problem? Well, we have in our toolbox a formula for parallel and normal forces. The force parallel, which is equal to the force friction, is equal to the force of weight times the sine of our angle, which in this case happens to be 30 degrees. And the normal force, well, that's equal to the weight times the cosine of 30 degrees. So mu, which is force of friction divided by normal force, is just the weight times the sine of 30 degrees over the weight times the cosine of 30 degrees. So it turns out that the answer to this problem doesn't really depend on how much it weighs. That 500 newtons could be replaced by 50 newtons and we get the same answer. It's really just sine of 30 degrees over cosine of 30 degrees. This is really equal to the tangent of 30 degrees. So mu is equal to the tangent of 30, which is 0.577.